Hello everyone. I'm switching back to the more massive black holes now, going back to the black holes that will be sources of gravitational waves for current and future experiments. And I will basically build up on the talks of Marta and Monica in many ways. When I say massive black holes, I am not meaning just the massive LIGO black holes, were more massive than the black holes we thought we had. I'm talking about really, really massive black holes, with masses up to several billion solar masses. These were first proposed as the engines of quasars. This is a compilation of some results showing the distribution of luminosities and masses for some higher chemicals. And you see here they go easily to about 10 solar masses. But we have lower mass, lower luminosity, black holes with lower mass that power faint HN. This is an example from the local universe. This is the galaxy POX52, which has a mass, black hole mass of less than 6 solar masses. So there's really a wide range of black hole masses, and what I want to discuss with you today is how gravitational waves can really probe this whole range of masses and give us constraints of different types. So this is a compilation, as of a couple of years ago, of all the black holes that we knew in the nearby universe, with at least an estimate of the black hole mass. It's a few hundreds, days. So here, what I want just to highlight again is the range of masses that we have, from about 50,000 solar masses for the smallest black hole that we know today, RGG 118, to the most massive ones, more than 20,000 solar masses. Now, this is a really wide range, and indeed, what to me is astonishing is that with gravitational waves we can probe this whole range. Not only will we can probe this whole range, we will probe also the cosmic history of these black holes. So this was discussed already many times. We can use the frequency of the elastic orbit to connect the black hole mass to the frequency at which we see them. So that's why LIGO sees small black holes, or at least small black holes for our standards. LISA will see more massive black holes, about 10 to the 6 solar masses, which, as you see, is right in the middle of the distribution of masses of the black holes that we know today. And pulsar-tuning array, going to even lower frequencies, goes to more and more massive black holes. And we can see those that perhaps powered quasars at high redshift. So this is a figure that I stole from Monica, putting these in a more general context, in the sense of how many of these black holes we expect as a function of their mass, and how different instruments from LIGO to LISA to PTA will probe different regimes in mass. And really, at least with LISA and PTA, for our massive black holes, we really have a picture of the full population. But even more importantly, we don't cover only masses, but we cover only also cosmic history. This is a classic figure from one of these several incarnations of the science case for LISA, where we show the redshift as a function of mass with the signal-to-noise ratio. And you see here, as I think a couple of weeks ago at the LISA consortium, it was said that LISA has a ridiculously high signal-to-noise ratio. I mean, it's incredible if you look here. You can then detect black holes up to redshift 20 and beyond. The question is whether we have them. So LISA can really probe the whole universe that we know. And here I compare also with probes in the electromagnetic spectrum. Here I included also future missions like JWST and Athena. We can get to redshift about 8 for black holes, down to about 10 to the 4 solar masses. Of course, we get the low mass black holes on the redshift. And finally, with pulsar-timing arrays, we probe the most massive black holes at a slightly lower redshift. So you see here that if you think of this in the context of the evolution of the universe, we are really seeing different types of systems. We start from the proto-galaxies, the first black holes that organize the universe, that created the first light, and we get all the way to black holes like black hole in M87 and in galaxy cluster. So we really have a complete vision of both the mass range and the redshift range. But not all galaxies are equal, not all black holes are equal. During the cosmic history, galaxies evolve in different ways. So here, for instance, I show some images from the galaxy zoo of galaxies with different masses. These are low-mass galaxies, about 10 to the 10 solar masses. And these are more massive ones, 10 to the 11 solar masses. What you should notice is a striking difference in colors. You may not notice this very clearly with the projector, but these galaxies are much bluer, and these galaxies are much redder. This means that these galaxies are forming stars actively. They have still gas that they can use for star formation, while these galaxies don't. Also, as we go to more massive galaxies, we start seeing more and more dispersion-oriented systems and fewer disks. Now, what is the relevance of all this for gravitational waves from massive black holes? That if we're looking now at high-mass galaxies, we're also looking at galaxies that are typically gas-poor, where stars make most of the mass, most of also the dynamical objects that the black hole can interact with. So in high-mass galaxies, where we have high-mass black holes, because I showed you that black hole mass scales with galaxy mass, we expect to have a different type of dynamical evolution compared to low-mass galaxies. So in a nutshell, what we expect to see is that in high redshift galaxies that are typically small in mass and also small in size, we have plenty of gas that is available to form stars, but also to interact with the black holes when they are there. At lower redshift, when galaxies is consumed, more a fraction of their gas to form stars, and they've grown in mass, then we become more stellar dominated, both in terms of dynamics and in terms of perhaps feeding the black hole. So we have different dynamic evolution. Monica stressed the difference between the interaction of black holes with stars and with gas. And we also have different probes. So we will need to connect the dots in the various redshift and mass ranges to have the full picture. So with LISA, what we can do is to detect massive black holes up to the highest redshifts. If there is a black hole out there, we will see it. Well, it is in a binary. But really, it can probe cosmic times that are inaccessible with anything else. And this, for someone like me who works on black hole formation in the very first galaxies, is extremely important. We don't have any other way of seeing them at the spot when they form. We can only see the archaeology today. With PTA, we're proving something different. We're probing massive black holes in massive galaxies at low redshift. In this case, what we're really probing is the dynamics in a stellar-dominated system in a mature galaxy. Not only, what we will also have is that we want to test whether our conjecture that the most massive black holes are mostly built up by mergers is true. And I will get back to this towards the end of my talk. So how can we go and compare our theoretical expectation to gravitational wave experiments? Now, as Maura said, we don't have detection yet for PTA, and LISA is not here yet. But so what we can do is to build a framework so that we can compare models with upper limits or observations from the Earth. So the way we go is to use the full population of black holes that we have in our models, different models. By the end of my talk, I will compare all the published models with predictions for black hole mergers and try to infer what the real population is by comparing with the analysis of the population that we have. Now, I will show you here an example. This is a slide that Alberto Cesana sent me just last week to share with you on purpose, in which he can show you what we can already do with PTA experiments. Now here, the y-axis is the strength of the signal at a frequency of 1 year. And here we have the calendar year. Each one of these colorful points and lines is a different theoretical model. From the early ones, you can see all the reference here, to the most recent ones, including, for instance, also three-body interactions. Here, the gray area shows the current limits. And here you see the PDF, the distribution of the probability from the different models. So as Maura was saying, we are already eating into some of these models. We are already excluding some of the models. There's still much freedom. As Monica showed very clearly, there is much uncertainty in the dynamics of black holes. When I said that black hole mass scales with galaxy mass, I gave you something like 10 to the minus 3, 10 to the minus 4. So we still have also freedom in understanding the relationship between black holes and galaxies. We don't expect that each black hole and each galaxy know about each other with an extremely high degree of precision. But so this is the type of approach that we want to have. We have theoretical models that we can compare with observations. And the good thing in this particular field is that really theoretical models are being built up now so that we can compare clearly the observations with the theory when we have it. So in terms of theoretical models, what is it that goes into these models? What do we have to assume, and how much certain are they? Well, there are a few things that we know, the basic ones. We see black holes at high redshift in powering quasars. We see black holes in galaxies today. So we expect that as a function of time, from early galaxies to today, both the black holes and the galaxies have evolved, and perhaps, hopefully together, but not necessarily. One of the two may have evolved before the other. So this is everything that we have to include in our models. We have to include the evolution of the universe. We have to include evolution of galaxies. We have to include black hole dynamics, black hole formation, black hole growth. And so if you think that stellar evolution is complicated, welcome to my world. So this is just an example of what we think are the main ingredients of what goes into merging two black holes. So we have to start with the cosmological context. So since I said, especially for LISA, this is very important because we are seeing black holes at the very highest redshifts. So we have to start with simulations of different kinds that cover wide volumes all the way to high redshift. Then we look at galaxies merging together. Here we are still talking about scales of hundreds of kiloparsecs down to about 1 kiloparsec. As Monica said, black holes actually start emitting gravitational waves effectively when they're at about milliparsec separation. Dynamical friction brings the two black holes from hundreds of kiloparsec away, each in its own galaxy, to forming a binary, a bound binary at the center of the remnant. Then at this point, there is a bit of magic, a bit like Ilya said. There are many different ways of thinking of what happens from the separation when the binary forms, about 1 parsec, to when gravitational waves take over. Now, dynamical friction is a clean process. As Fred said, it's nice dynamics. Dynamical friction is clean. You can understand it well. Gravitational waves, you can understand them well. In the middle, there is a bit of everything, mostly because if we had only stars or only gas, we could model it well, but it's a mixture of two, and this makes a very complicated problem in terms of simulating it, but also from the analytical point of view. So what we need to first predict and then interpret the gravitational wave signals that we see from massive black holes are basically 3 ingredients. How many galaxies host massive black holes? Because the merger rate will depend on the number density of black holes squared, basically. So when, where, and how black holes form. How long it takes for black holes to merge in a given galaxy. So the dynamics of black hole mergers that Monica already described. And finally, how black holes grow in mass over time. How do they move from outside LISA's band to LISA band and then to PTA? So this happens because of accretion of external gas, but also mergers with other black holes. So I will quickly sweep through the uncertainties more than the certainties that we have in this field. This is a figure that summarizes our current knowledge of black hole formation, meaning that I collected most of the models that are out in the literature for black hole formation in the first galaxies. I haven't included primordial black holes here, but they are also an option if you like inflation. So you see here that we have a mass range that is very wide, from a few tens of solar masses up to 10 to the 6 solar masses, perhaps. Here, metallicity is the y-axis, and you can read this just as a cosmic time. Low metallicity or no metals is early universe, and then we get to solar metallicity today. So we have processes that create black holes in the early universe, and processes that can, in principle, create black holes all the way to today. These are some examples showing how the number of black holes that you form and their masses, so this is just, if you take the same models for black hole evolution, except for the initial mass, how much does the merger rate predicted change? And you see here that the change is several orders of magnitude. Unfortunately, this is one field where we don't have much constraints and where we really think that we need LISA to put constraints in the models rather than vice versa. And we don't even know if stellar mass black holes can grow enough to become massive. Then we go to dynamics. This is just a summary of basically everything that Monica said, that when two galaxies merge, you cannot expect that 99.9% of the black holes will merge as well, depending on the mass ratio, which is the main criterion, and also on the dynamical properties of each galaxy, in particular how dense they are. You may have a successful merger, so the two black holes eventually find each other at the center of the galaxy, or we have a failure. And in this case, you will have a population of wandering black holes in galactic halos. Now, this production of extra black holes beyond the central one is a generic prediction of all models where black holes are allowed to evolve dynamically, not just anchored in the center and put there. Black holes fail to merge at times. And then there is all this complicated physics in the central parsec, where we expect that black holes can find each other successfully after forming a binary over a few 100 million years. But we don't have a single model that studies all the possibilities in one go. So this said, you can create your own population of massive black holes. In this case, I show the evolution of a population of black holes from a series of simulations that I've collected from my group. We have some small black holes that don't grow too much, and then eventually they start growing a little bit at low redshift. This is a very generic result of models. Black holes in a small galaxies at high redshift have a very hard time finding the dynamical center of the galaxy and eventually grow in mass. On top of this, you have supernovae exploding all over the place, and these supernovae eject the gas or energize the gas, and so the black hole is far from the center and in regions of low density, and so typically they don't grow much. Other black holes can grow more and get to the PTA range. So what is the prediction of the merger rate? Now, this figure is a success. Here I compiled predictions for the PTA range from semi-analytical models, simulations, empirical models based on observations or treatment of observations. And in the PTA mass range and redshift range, they agree incredibly well for our standards, within a factor of 3. Let's go to LISA. not the same picture. Here the difference is about 2 orders of magnitude between models. Why is it? Because we do not have constraints, observational constraints, to anchor our models at high redshift. So we have total freedom. Of course, electromagnetic observations in the near future, and I think especially JWST will be very useful, will help us weed out the models that don't make sense. But really, I think that this is what's showing LISA's discovery space, things that we cannot reach in any other way. And so in summary, this is really interesting, cool, and everything. At the moment, we have more questions than answers, and if you wait a few more years, I think we will have answers as well. I think black holes and gravitational waves together are really promising a great future of discoveries beyond what LIGO has already done. And I will also leave you here with a movie. Thank you.
Thank you, Bert. Time for a few questions. Charles.
So excuse my probable ignorance here, but how much do you think you know or actually know about the progenitor masses, the very first masses of black holes?
Well, we have an uncertainty of about 5 orders of magnitude.
Okay.
We really don't know what. We have different processes that can be at play. They can be mutually exclusive or not. Now, I think that nature has been wise in providing us with these black holes. We haven't been able to figure out exactly what nature has thought at the very beginning. But so the models exist, and they're well developed. We don't have constraints. This is the main problem.
Other questions? Let me ask one. It's likely that the very first mergers are going to be from smaller mass black holes unless direct collapse solves the problem. Has that been factored into the LISA sensitivity estimates?
Well,
because we don't know, basically Charles's question, we don't really know.
Well, LISA is agnostic compared to black hole masses. So the sensitivity curve just tells you if you have these masses, I can see that or not. Okay. 100 solar masses is a bit hard, I would say. Mm-hmm. So for that, it's much better to have something like the Einstein telescope. So as I think Monica was saying, most likely LISA, the bulk of detections will come from the cosmic high noon, but the few ones that we may have at high redshift will open a range that we cannot access in other way.
Yeah. Other questions, comments? Nobody? Yes. Yeah.
So to elaborate a little bit on that last point,
yeah.
100 solar masses seems small for you, and that's all I seem to see in these plots. But is there a reason for 100 as opposed to 10 or 30?
Yes. Well, at least in my opinion. If you have a black hole with a mass of 10 solar masses in a galaxy, it's just a black hole with a mass of 10 solar masses in a galaxy. So it could be anywhere in the galaxy. This will never grow to become supermassive. So I care about the black holes that it will eventually grow to become supermassive. For this, you need a black hole that is sufficiently massive that can fall into the deepest point of the potential well and be fed with gas and stars. For this, you need a black hole that is at least a factor of 10 more massive than all the other black holes. Just because you need some dynamical friction to get it to the center. We are not living in a very dense stellar environment like Fred described. So I would say that in a galaxy with a mass of 10 to the 5 solar masses, in a halo with a mass of 10 to the 5 solar masses, 100 solar mass is a very minimum that has some dynamical importance. The bare minimum. I'm coming to the conclusion with several numerical experiments, 10 to the 4 is a better number for the black hole to actually grow and become supermassive.
Okay, if there are no other questions, let's thank all the speakers in the session again.